Hello and welcome. This is Geology Basics Video Mini-lecture number 2, in which we focus on the science of geology. Geology is the science that studies Earth and how it works, the past, the present, and the future. We'll focus on two main areas here. First, what is included in geology and what do geologists study? And also, what characteristics of the science of geology make it unique? Everything in this class centers on learning goals. Learning goals are what you are expected to be able to do as a student after lots of practice and instruction. And so the learning goals listed here are what you're expected to be able to do after working your way through this video lecture and also the textbook areas that overlap. So first, what is included in geology? First, list at least 4 topics that geologists study. Second, name at least 2 specialties within the field of geology and identify what they study. The other question we're trying to answer is what characteristics of geology make it unique? So our third learning goal is identify 4 aspects of geology that make it unique amongst sciences. And 4, explain the geological concept of uniformitarianism. Quite a mouthful, one of the main principles that really sits within geology and is used to apply. So we're going to start learning it this week.
Here's a sampling of topics geologists study. It includes glaciers, climate, volcanoes, Earth's interior, earthquakes, plate tectonics, minerals, rocks, oceans, streams, other surface processes like weathering, fossils, and Earth's history. Are there any surprises here for you? One area that's definitely related to geology but generally considered separate is meteorology, the study of weather. So you won't see it included here, and it will not be a topic of the course. Geologists do study past climate and how it's recorded in rocks and minerals and sediments, but climatology, truly the study of the modern climate, is also usually considered outside geology. Most professional geologists have master's degrees, which means at least 6 years of college education, and most of us specialize in one area or another as grad students, graduate students, or even undergraduates. Common geology specialties include energy geology, environmental and engineering geology, geochemistry, geochronology, geomorphology, geophysics and seismology, geoscience education, hydrogeology, mineralogy, planetary geology, petrology, the study of rocks, sedimentary geology, soil science, structural geology and tectonics, and volcanology. For example, geologists who are interested in Earth's structure, earthquakes, and how to use seismic waves to understand shallow or deep layers of Earth have different training than geochemists or sediment and soil specialists. And you thought all geologists were just geologists, right? Let's take a moment to check up on your understanding. Geology includes a long list of things related to everyday life, but one of the examples here would not be considered part of geology. Pause the video while you read and consider the question and answers, and then play it again to learn the best answer. How did you do? Ice storms are considered weather, so they're not usually considered part of geology, but all the other options here are a way your life could be impacted by geology on a day-to-day sort of thing. Geology has aspects that make it unique among all the sciences. We'll discuss 4 major aspects that make it unique, and also an important type of reasoning used in geology called uniformitarianism. Kind of sounds like a religion or some sort of fringe belief, but it's actually not. It's a big part of how geology works. One of the aspects of geology that contributes to its unique identity is that it includes study of objects that are tiny, like individual atoms and molecules or groups of atoms bonded together, all the way up to entire planets. So as a geology student, you'll practice considering how things happening at one scale influence what occurs at other spatial scales. To illustrate this, let's take a tour of the geology of a mineral you all know, a diamond. We'll start at the atom scale and we'll move our way up to the continent scale. At the atomic scale, we've got a model here of how the carbon atoms making up diamonds are organized and bonded together. These properties give diamonds their unique characteristics, like being the hardest natural material. Going just slightly larger in scale, individual diamond crystals can be microscopic to sort of fist-sized or larger. This crystal shows one of the characteristic three-dimensional diamond shapes that they come in. Going larger in scale, diamonds commonly form in rocks called kimberlites that are igneous rocks, that is, rocks formed where molten rock or magma cools, often related to volcanic systems. Kimberlites often have a green color to them, at least in part, because they also contain a mineral that makes up most of Earth's mantle called olivine. You'll get to know olivine pretty well. Going still larger in scale, let's take a look at what a diamond mine typically looks like. Diamond mines are often huge pits dug into the ground that get narrower as they get deeper, as shown in this perspective view of photograph. Mines have this shape because kimberlite usually forms as a volcanic pipe, the conduit through which magma flowed to the surface, and then some erupted as lava. Diamonds formed in the bottom of the pipes, and so the mines are built to go straight down into the kimberlite pipe deposit. Kimberlite rocks and volcanoes don't form today. They only formed in Earth's ancient past, during a period of time known as the Archean. That was about 4 billion years ago until about 2.5 billion years ago. So, geologists who want to find diamonds need to know all this. In order to find likely diamond deposits in kimberlites, you're going to start by identifying rocks of Archean age, shown in orange on this map. The closest large area of deposits to us are north of Lake Superior in a geologic province called the Canadian Shield. So that's where I would recommend going to look for diamonds, if you're apt to do so. A second aspect of geology that makes it unique among sciences is that we study processes that occur very quickly, in seconds, even fractions of a second, all the way up to those occurring over billions of years. 5 examples of processes here illustrate this big difference in timescales. Earthquakes occur in seconds or even milliseconds, up to minutes. Flooding, which in our area is the most common geological hazard, take place over hours, days, to weeks. Mountain building is a process that takes hundreds to thousands of years, in some cases millions of years, to happen. Erosion of built-up mountains takes place over even longer time periods, hundreds of millions of years. The nearest mountain range to us is the Appalachian Mountains. The ones we see today are tiny remnants of much larger mountains that formed nearly 500 million years ago. And the movement of tectonic plates to form and break apart continents that in part build mountains like the Appalachians. This process takes millions to billions of years to happen. A third aspect of geology that makes it unique is that it has its own set of laws and principles, but it also incorporates reasoning and concepts from a variety of other sciences. On the left-hand side, I have a diagram that shows geology is situated kind of in the middle here, and so it shows it's closely related to chemistry, astronomy, biology, and physics. And you'll notice some of the same terms as we encountered looking at geologic specialties, such as geochronology, geochemistry, and geophysics. Another visualization I really like about geology is on the right-hand side. This is by the artist Ray Troll. It shows a geologist and an artist traveling in a field vehicle over many layers of buried fossils and rocks, and states the data is in the strata or the strata. And that means that geologic data is contained in rock and sediment layers called strata or strata. An important part of geologic reasoning is often stated as the present is the key to the past. Take a minute. Here's the basics of the present is the key to the past. Geology includes the study of how modern systems on Earth, such as this river system, work. Geologists apply what we know about how things work today to the past, and also look ahead to what it might mean for our future. Our example here of a system is the Platte River. The Platte River is a major river that drains water and sediments from the Rocky Mountains of Colorado and Wyoming across the Great Plains, where it links up with the Missouri and then the Mississippi rivers. By understanding how rivers like the Platte erode, transport, and deposit sediment, geologists have been able to interpret a great deal about past river systems, including the one pictured on the right here. This is a set of rock layers called the Morrison Formation, and this is in the western United States. You might not yet have heard of the Morrison Formation, but it's famous worldwide for Jurassic-aged fossils of dinosaurs. If you've ever heard of a dinosaur from the United States or North America, chances are it's from these set of rock layers. Geologists are able to make these connections because we rely on our field's close relationships with other sciences. We are able to assume that fundamental physical and chemical processes work the same over time. This principle is constantly tested to make sure it's really true, and we call it uniformitarianism, that some things can be considered uniform or the same over time. The fourth and last major aspect of geology that we'll discuss that makes it unique is that we work on visualizing and understanding things that cannot be directly observed. So, how does this relate to uniformitarianism? What if we can't directly observe something today that we want to understand and study? We have lots of creative ways to do this in geology. One way is to run lab experiments and build models of systems that don't exist today. Our first example on the left is a huge classroom-sized river model called the Jurassic Tank. So this is a really cool facility that I've had a chance to visit in my past. The Jurassic Tank is a facility that models when sea levels were much higher in Earth's past than they are today and how this impacted rivers. So the Jurassic part of Jurassic Tank is because the Jurassic time period is also a time when sea level was higher than today. So this giant model allows geologists to run experiments to replicate those conditions of the past at a smaller scale than real life. What about conditions deep in the Earth? We'll soon be working on Earth's layers, and you'll find out that most of what we know about them is through indirect evidence. We can't physically go there, but we can indirectly know a great deal about their properties. One example is a really neat experimental device called a diamond anvil press, in which we can squish minerals and other materials to the same pressure conditions as, say, in the Earth's mantle, and this really has helped us understand better what minerals exist there, and that in turn helps us understand other properties of those layers of Earth. So these examples illustrate how we can apply the idea of uniformitarianism even when we can't directly observe what's happening today, and how that relates to what happened in the past. And last but not least, let's check in on how well you remember what uniformitarianism means. As usual with questions, I'm going to ask you to pause the video while you consider carefully reading all the answer options, and then play again when you're ready to learn more. So how did you do? D should be the best answer here, that uniformitarianism means that fundamental chemical and physical processes work the same way in the past on Earth as they do now, and this is one of the guiding principles of geology. We always test this, but we can count on it, and so far that's what we've learned, and it helps us interpret conditions that don't exist on Earth today. That's it for now. See you next time.